Chapter 1, Direct Current, DC. Students majoring in electronics always start with a direct current, DC, class. DC is a basic electronic theory that you must learn and understand well. This is the first step to a successful career in electronics. Let's first define some DC parameters. Current. Electrical current is quantified as change, increment or delta, of electron charge, Q, with time. Think of it as flow rate in plumbing. Measure of charges, increment Q, flowing through a point, node, with time, see figure 1.0. Current's unit is amperes, A, with I being its symbol. Electrical current is of the number of electron. Current equals increment Q/time resistor. All materials possess resistance, which is a measure of the amount of resistor value. A resistor is a passive electronic device made exclusively for electronic systems. Resistors resist current flow for a given electrical voltage. Voltage will be defined shortly. A passive device by definition does not generate energy but rather stores and/or dissipates energy. The most abundant materials used in resistors are copper, Cu, and aluminum, Al. Carbon, thin film, metal film, and wire wound are popular resistor types. Resistor size, resistance, is measured in unit ohms with R as the symbol. Resistors come in many physical forms. Wire leads, surface mount, integrated circuits, ICs, package are popular ones. Figure 1.1 on the next page shows a graphical view of a copper, Cu, wire bundle with a certain length and area exhibiting a finite resistance amount. Internet wires and cables found in residential and commercial dwellings are largely made of copper with a plastic shield on the outside. A resistor can be discrete, one device per item, or manufactured via an IC process housed in an IC package. We will explore more on semiconductor packages later in the chapter. Resistance for a given material strongly depends on the resistor dimension, where resistivity is unique to the material's type. Figure 1.0, Increment Q/time. Figure 1.1, Copper wire. Common carbon resistors are measured in the order of several centimeters, see figure 1.1a. Figure 1.1a, Carbon resistors. Due to the small carbon resistor sizes, color bands are used to indicate resistance values instead of printing them on the resistors. There are 4 bands. The first band on the left represents the first significant resistance digit. The second band is the second significant digit. The third band is the multiplier, and the last is tolerance. Tolerance determines the maximum percentage change in resistance from its nominal value. Table 1 shows the details among band color, digit values, multiplier, and tolerances. Table 1 Resistor band color, digit values, multiplier, and tolerances. Let's apply this to an example. What is the resistance of the carbon resistor that has brown, orange, red, and gold bands? First, brown yields 1, orange means digit 3, red multiplier means 100, gold represents 5% tolerance. The resistance is therefore calculated as 13 times 100 is equal to 1300 ohmega or 1.3 k ohmega with 5% tolerance. Figure 1.1b, Surface mount resistor. Surface mount resistors, on the other hand, are popular due to their miniature sizes. They are ideal for portable applications when small size is necessary. Figure 1.1b shows several surface mount resistors. A surface mount resistor can be measured as small as 0.2 mm, millimeter, x 0.4 mm, millimeter. Because surface mount resistors are small, in order to determine their values, numbering codes are used instead of color bands. The numbers printed on the resistor are usually 3-digit numbers. The first 2 numbers represent the first 2 digits of the resistor values, while the third digit represents the number of zeros. For example, a resistor marked with 203 means 20x 1000 ohms or 20 k ohmega. A 105 resistor gives 10 by 10 5 ohms or 1 mΩ. Resistors manufactured by microelectronics technology use different methods to determine resistances. Depending upon the chip manufacturing process, there can be multiple resistor types, ranging from metal and thin film to polyresistors. The resistances are determined by the vertical and horizontal dimensions in conjunction with the sheet rho, pronounced as rho resistance. Sheet rho's units are in omega per square, omega/square. For example, a bipolar CMOS, BiCMOS, process thin film resistor's sheet rho is specified as 1000 ohms/square. Length/width defines the square numbers. If the resistor's length and width are drawn as 10 micrometers, by 10 micrometer, respectively, the number of square equates to 10. /10 equals 1. The resistance is then calculated as. Regarding the chip manufacturing process, in addition to sheet rho resistances, each process offers a slew of devices with a unique set of parameters. Below are some common ones you will likely encounter. Transistors' minimum geometries. CMOS uses gate length, where bipolar transistors use emitter width. Transistors' maximum operating frequencies. Capacitors' capacitance per unit area. Temperature coefficient. It determines how much variations device parameter changes with temperature. Maximum voltage supply and breakdown voltages. Transistors drawn versus manufactured dimensions. Metal level numbers available, and many more. Further explanations of these parameters will be discussed later in this book. Full understanding of these parameters is necessary before deciding on a process to use for a particular chip design. Further details on microelectronic design will also be discussed in later chapters. Voltage. Voltage is the potential difference, subtraction, between 2 points, nodes. The object of these points can be any material. The most common materials are electronic devices such as resistors, diodes, and transistors, which are the main focus of this book. Each electrical parameter has its own symbol and unit. They are summarized in Table 2, 1.